Hello, my name is HAMIZAN SALLAHUDDIN and I will start with introduction. Electromagnetic crane operates based on the interaction between electric current and magnetic field. When current flows through a coil, the magnetostatic field is produced around the conductor. The presence of ferromagnetic core inside increases magnetic flux density by concentrating the field line. Unlike a magnet, the magnetic force can be controlled electrically by switching the current on or off. This concept widely applied in industrial lifting system, relay, motor, and actuator. Next, objectives. Design and construct a simple electromagnetic crane using a coil and ferromagnetic core. Demonstrate practical application of current-induced magnetic field. Number 2. Investigate the relationship between electrical parameter and magnetic strength. Study how number of turn, current, and permeability affect the magnetic field and lifting force. Number 3. Apply electromagnetic field theory learned in BERG 3743. Illustrate concepts such as Ampere law, magnetostatic, and magnetic flux density. Number 4. Analyze limitation and improvement in real-world system. Examine why the electromagnetic can lift only a limited load and propose enhancement.
The component that I use for this project is iron nail. Iron nail acts as a ferromagnetic core that concentrates the magnetic flux and then increase the magnetic field strength. Copper wire forms the solenoid coil which let the current through and create the electromagnetic field. For power supply, we use two types of different battery. The first is the 9-volt battery and then a 12-volt battery. And then we have a switch which can control the current. With button, we can activate or deactivate the current flow to the coil. And then finally, paper clip that act as a load, which we can measure the strength of the magnetic field using different battery. So first, we need to make the electromagnet. So we use the iron nail as a core and then wrap the copper wire around it neatly and tightly because it's important on creating a magnetic field. The more neatly and tightly we wrap the core, the more stronger the electromagnetic becomes. Also, we leave the ends of the both sides of the copper wire so that we can attach it to the supply. So how do we set up the experiment? We use three types of situation. The first one is with 9-volt battery. We use direct connection from the battery 9-volt to the coil. The solenoid is connected through a series circuit to the battery. And then we use direct connection to the 12-volt battery. But now, because the voltage is higher, there is more current that moves through the coil which make the magnetic field is more stronger. So the 12-volt we get higher pickup of the paperclip than the 9-volt. For our final situation is that we add a switch to our 12-volt circuit which we can control the current flow to the coil from the battery. When the switch is off, there is no current flow to the coil, so the magnetism will not happen. But when the switch is on, the current flows to the coil and the magnetism happens. So this works like a real electromagnetic crane in real life.
I will talk about operating principle. When a direct current flows through a coil, it produces a magnetostatic field around the conductor. So this right here, we can see a coil. According to Ampere law, the strength of the magnetic field is directly related to the amount of current flowing in the coil. The coil therefore behaves like a solenoid, generating a magnetic flux along its axial direction. By inserting an iron nail into a coil, the magnetic field is significantly strained because the nail acts as a ferromagnetic core that concentrates the magnetic field line. So this here we can see a nail in a coil. As a result, the magnetic field strain is proportional to the permeability of the core, the number of a coil turn, and the current flowing through a coil, which can be expressed as B proportional to mu and I, which is N is the number of turn, mu is the permeability of the core, and I is the current. As for the result, in this project, two power sources were tested. Using 9V battery, the electromagnetic was able to lift only one paperclip due to a limited current and a weaker magnetic field. When a DC motor battery was used, the higher current produced a stronger magnetic field, lifting the paperclip more effectively. When the switch was used to control the electromagnetic, when the switch was off, no magnetic attraction occurred. When turned on, current flowed through a coil, and the electromagnetic lift the paperclip. Switching off collapsed the magnetic field and released the load. This miniature crane imitates the operation of real industry electromagnetic crane. The coil generates a magnetic field to magnetize the iron core and lift metallic load, while the switch functions like the operator control, turning the magnet on and off. Although scaled down, it demonstrates the same fundamental principle as a full-size crane.
Limitation and analysis. 9V battery. We use 9V battery supplied with low current, and we using thicker copper wire limits number of turns. Low Newton result in weak magnetic field. Coil length alone does not determine magnetic strength. And proposed improvement. Use thinner copper wire to increase number of turns. Replace 9V battery with AA battery for higher current. Use soft iron core with higher permeability. Minimize air gap between load and core. This project successfully demonstrated that fundamental concept of an electromagnetic crane using a current carrying coil and ferromagnetic core. The results confirm that magnetic field strength depends on electric current, number of coil turns, and core material properties. Although the lifting capability was limited, the electromagnetic concept operated as expected. Overall, the project strengthened the understanding of how electromagnetic principles are applied in practical engineering system. Thank you.